Hi everyone, my name is Genta from the Hong Kong University of Science and Technology. Today I will present our paper on are multilingual models effective in code switching. First, I will introduce the motivation of this work and describe some existing approaches in code switching representation learning. Then I list the datasets and tasks we use for evaluation in the experiments, and I will end the presentation with a conclusion. We recently observed that multilingual language models such as multilingual BERT and XLMR achieve very promising performance on natural language understanding tasks, especially on low resource languages. Yet, despite the enormous number of studies in multilingual NLP, only very few focus on code switching. Precisely, there is no comprehensive study investigating the effectiveness of the pre-trained multilingual models. Thus, the effectiveness of these multilingual models on code switching tasks remains unknown. In this paper, we explore following research questions that has been around for years. First, does larger multilingual models always perform better in code switching tasks? We can answer this question in two different aspects in terms of performance and speed or memory usage. Second, we also want to know which models are more effective in representing code switching text in deep learning framework. Should we use large pre-trained language models and sacrifice the speed by having low slow training and inference time for performance? Or should we use word embeddings that are more efficient for practical usage that might already have decent performance? As the response to those questions, in this work, we establish a benchmark to compare the effectiveness of multilingual models on various code switching tasks. We perform evaluation in terms of performance, speed, and number of parameters to measure the practicality of each model. So we take each pre-trained model, fine-tune the model with code switching training data with supervised training objective, and test them by using a standard test set. In this experiment, we compare four different types of approaches. First, we train bilingual word embeddings using Muse by taking fast text word embeddings from metrics and embedded languages. For example, English Spanish tasks, we take English fast text and Spanish fast text models and we align them in both ways. The second approach is multilingual language models, which is one of the most popular approach to code switching right now, such as using multilingual BERT or even larger model like XLM or Roberta, XLM, or the recent published model called char to subword. The third one is meta embeddings. Meta embeddings is a common approach in code switching to build an ensemble word embeddings from different language sources, and it uses an attention mechanism or concat or linear addition to combine representation from different sources. The last but not the least is the hierarchical meta embedding. This approach is the extension of meta embeddings and utilize not only word meta embeddings but also utilize subword level and character level embeddings and mix them into a single representation. To further improve the performance, we also built an ensemble model of meta embedding model, which is considered as a very efficient model that can improve the robustness of the model. We evaluate our models on 5 downstream tasks in the Lynch benchmark from Aguilar et al. 2020. We choose 3 name entity recognition tasks in Hindi English, Spanish English, and modern standard Arabic Egyptian, and other 2 part-of-speech tagging tasks in Hindi English and Spanish English. This is the result on the validation set. As you can see in the figure, using pre-trained language model greatly improve the performance in general. And we observe that Muse model do not perform well, and we assume that the word alignments do not help in representing mixed language sentences. Then it's also clear that increasing the size of the model tends to improve the performance, like in the case of XLMR. XLMR large outperforms the base model, but does not apply to XLM MLM large that has much more parameters compared to XLMR base model. It's also worth to note that chart 2 subwords surpass MBART that indicates the effectiveness of applying second pre-training step of MBART. Then you can see that meta-embeddings are far more efficient compared to all other models, and they achieve competitive results to XLMR models, which we can consider as effective models to be used in the practical purposes, while achieve considerably good performance in general. We also want to show the result on the test set in the Lynch benchmark. As you can see in the figure, The HME ensemble is on the top left corner of the figure, and it can be considered as the sweet spot between performance and the number of parameters. And we want to show in the table that XLMR large models actually use 13 times more parameters, and while it only improved 1.8% performance compared to HME ensemble model. In addition, we also compute the activation memory consumption on the GPU. Models using word embeddings are far more efficient because they only need to run few tensor operations. While for contextualized language models, since they have multiple dense layers, they need more memory to store the intermediate results. Finally, we will summarize the key takeaway messages of this presentation. A pre-trained language model does not necessarily guarantee high quality representation of code switching. Larger language model is relatively better, it does not apply to all models. Large models achieve the state-of-the-art performance on code switching, but with a huge cost in the inference time, and it has 13 times more parameters than meta-embeddings. And we also want to emphasize that meta-embeddings models are both efficient and also effective. They are in the sweet spot between the performance scores and efficiency, as we mentioned before in the previous slides. This completes the presentation. Thank you so much for your attention, and I will be happy to welcome any questions from the audience.